When we talk about reflection and refraction and diffraction in the next chapter, when we go through how optics actually work, one of the things that we need to talk about as kind of a prelude to get into that is how light travels or how it behaves when it interacts with matter in the first place. And I think I had asked you guys to remind me to start off the discussion today with absorption and resonance. When we think about how light interacts, let's go all the way back and start off with where light comes from to begin with. What is the original source of a photon of light?
Big Bang. An electron gets excited and then electrons fall back into the lower shell.
Yeah, exactly. So if we look at an atomic level, a picture that I'm going to draw up here is supposed to be of an atom. You guys have all had chemistry, right?
No.
Okay. So even though my picture won't be very good, you'll understand what I'm trying to show. So in the nucleus, in the center of the atom, you've got the protons and neutrons. It's going to have to be positively charged. For now, I'm just going to say that's a big positive chunk. Then, I've got these orbitals out around there where the electrons could be flying. How many electrons can fit in that first orbital? 2. First orbital is called the 1s orbital, and it can hold 2 electrons. So this orbital has 2 spots where there might be electrons in it. Then there's another level up here that can hold some electrons. And how many electrons can be held in the next level? Yeah. In the second level, you can have 2 of them in s orbitals and then 6 of them in p orbitals. So it's like there are 8 spots altogether. Now, my way of visualizing this, I always kind of thought of atoms like a parking garage. So you have the different levels are like the levels in the parking garage. So on the first floor, the lowest orbital, the 1s orbital, would be the first floor on the parking garage. And it's only got 2 parking spaces in it. And the second floor in the parking garage has 8 parking spaces in it. And the third floor, goes on from there. So when an electron, if you have an empty electron, you've just got a nucleus, and you start putting the electrons into it. For example, a hydrogen atom has 1 proton. It's only going to have 1 electron go in. So when the first electron pulls into the parking garage, well, what parking space would you take? Would you guys drive all the way up to the top floor and park if all those parking spots lower are available? No, you're going to take the first one you come to. So you're going to come in and you're going to park in the first floor. So that electron could stop right there in that parking spot. So then the second electron comes in. Well, where's the second electron going to park? Say, do you drive up to the second floor if you can park on the first floor? No, everybody parks closest. So the second one would go in to that spot. Third electron comes in. He pulls into the parking garage. Where's that one going to park? Well, first floor is full, so you go up to the second floor and you take the first one that you come to.
Yeah, is Ian Murphy in class today?
Yes, he is.
Could he come to my office at 11:30, please?
Okay.
Thank you.
Do you know who that was?
Yeah, that's what they got ready.
Okay. Like I said, I think that's Kathy Brinkmeyer.
Yeah, I'll miss all
All right, so third electron comes in, parks right there. Now, fourth electron comes in, pulls in, drives up to the second level. Is it going to park in that spot right next to that electron? If you pull into an empty parking garage and there's 1 car there, do you park in the spot right next to that car?
No.
No, because if you do, then they're going to hit you with their door, you're going to hit them with your door. You move over and you take one, you give them a little bit of room. Well, the electrons do the same thing also. The next one doesn't go right in there. The next one goes into this orbital. Then the next one goes into this orbital. Then the next one goes into this orbital. And then when they come in, now everybody has an electron already parked next to them. So now they start doubling up. So the next one goes here, and then here, and here, and so on. Now, is there any difference between those 10 electrons, parking spaces that I have shown so far?
Yes.
Like what might be?
The ones in the second orbital have more energy than the first orbital.
Yeah, there's a difference in the amount of energy associated with each parking spot. And when we get into our quantum mechanics unit, that's going to be kind of the big idea that we'll be talking about, is how much energy is associated with each one of them. For our purposes right now, it's enough to just say that there's going to be a different amount of energy associated. Now, let me pretend that we've got 2 levels completely filled, and here's a 3rd level that's completely empty. Suppose that somehow you zap some energy into this individual atom. You send in a photon of energy that hits just this atom, and this atom gets a little boost in energy. One of the things that might happen is this electron that's in orbit might move to a different orbit. Just like a space shuttle in orbit, if you give it a boost in energy, like if you turn on the engines, what's going to happen to the space shuttle's orbit?
It's going to pull away from Earth.
It's going to kick out to a higher orbit. It's going to pull away from Earth. Okay? So this electron may kick up to a higher orbit. So this electron right now that I've just drawn the X through isn't there anymore because it has kicked up here because it picked up some extra energy. But now there is a lower energy parking space available, so it might fall back. Can you see that we just had an electric charge move through space? It went from here to here and back. And what did we say was the source of all electromagnetic waves?
The movement of electrons?
A moving electric charge, when we just moved an electron from here up and back. So when that electron falls back, it falls to a lower potential energy source, and so that energy's got to go somewhere. Well, in Physics A, we talked a lot about, like in mechanical systems, if I give this thing more potential energy, and then I drop it and let it fall back, well, where did that energy go after it got back to where it started?
Sound and table?
Radiated off into the room in the form of sound. The air molecules vibrated. The temperature of the room went up a little bit. Just a second, let me make this point and I'll get your question. Now, if that, instead of being a roll of tape, was an electron that fell back, then, again, that energy has got to radiate somewhere, and so it turns out that energy radiates away in the form of a little photon of light. So a photon is like a packet of light that has a specific amount of energy, and the energy is associated with how far it fell when that electron that produced it moved inside the atom. So in fact, again, I'm kind of getting into our quantum mechanics stuff, but do you guys know how we know everything that we know about the structure of the atom? That we know that that lowest energy level holds only 2 electrons, and the next energy level out holds 8 electrons? How do we know that? Nobody's ever seen that.
Because of atoms being neutral and knowing that, like, it has to match the protons, and then doesn't it, like, get bigger or something, like, more, as you add more molecules or something?
Well, we think all that, but we haven't seen it. What did we actually see?
You did theories and experimentations.
Couldn't hear me, I'm sorry.
Theories and experimentations.
With light.
The experimentations part is what I'm after. What did we actually see?
Light.
Light. In chemistry, didn't you guys do the thing where you had little spectroscopes and you looked at flames and where you put different chemicals in them and you looked at the colors of light? To me, it's amazing that everything that we think we know about the structure of the atom came from looking at pretty colored lights. We looked at the pretty colored lights and we analyzed the different energy of those photons of light, and our whole idea about the structure of the atom, our whole model of the atom, is based upon the light that we saw from it. So this photon of light that comes flying away has a specific amount of energy associated with it, and it also then has a unique color. If it happens to be a frequency that falls in the range that the chemicals in our retina detects, then we say it's visible light and we see it. But that little packet of energy goes flying away, and we call that a photon. Okay, you had a question.
Yeah, I was just going to say, like, with, like, dropping the thing, doesn't some of that, like, force or energy or whatever go into the table with it, like, stopping it or something like that?
Yeah, it goes into, all the surroundings around it. And that idea kind of ties in here with where I'm going with this in terms of why some things are transparent and some things are not. If, keeping in mind what we've got there, suppose then this is an edge-on view of a pane of glass, okay? And suppose we could see the actual silicon dioxide molecules that make up this pane of glass. And this one, that's supposed to represent them. And here comes a photon of light that got emitted somewhere in the universe, and it's been traveling through space, and it reaches right here. When that photon hits this very first atom out here on the edge of the pane of glass, that atom will absorb the energy. And now one of two things will happen. It may just absorb that energy, and then the electron kicks up, drops right back, and emits another photon. And if it does, how much energy will the new photon have compared to the original photon that caused the electron to be kicked up in the first place?
A little less.
Turns out it's the same amount. It turns out that they're not a frictional loss in this case. You end up with the photon that it emits is like a twin of the original. Okay? So that atom, the photon hits it, the atom absorbs and re-emits a twin photon. Then, suppose that photon traveled in the direction into the glass. It might travel a certain amount of distance before it comes to the next silicon dioxide atom. But when it gets to the next silicon dioxide atom, if it's positioned there, that photon can hit it. And what's going to happen when that photon hits that second molecule? Same thing. That second molecule gets excited, the electron kicks out to a higher level, and then it drops back. And when it drops